The theme of this e-tutorial is to show how it is used the solid mating, a command allowing us to place a solid in relation to other ones by applying geometric constraints between the entities composing the solids. In particular, we will have a look at the different options of this command, while later we'll deal with the multiple mating command and we'll see how to check any possible interferences and collisions between objects. Let's enter the first solid, an external reference component framework, by a click at the point where we want to place it. We set visualization to shaded view plus boundaries. Upon positioning, we can choose to have the positioning cursor in the origin point, generated when the object was created, or at the center of the box overall dimensions of the object, as we are now simulating, selecting the relative option. We keep this setting, and we are going to add the next component, always with the sequence Insert Component X Reference, lever 1, and we insert it in the desired point. We adjust the view by the F key from the keyboard for Fit View. We rotate a little bit to watch better the objects. Then we magnify well the area where we're going to run the first mating. We have the object to be positioned, the reference object, then two flags, deferred mating and symbolic references only, the last one allowing to select only entities associated to symbolic references, while the first one allows to ask that the constraints we are applying will be calculated only upon exiting the command. We also get simple mode and inferred mode. Simple, we apply a constraint at a time. Inferred, when we define object and reference object, the program offers us all the constraints as possible and compatible with the two selected objects. We start with simple mating, so between the pivot of the lever and the whole of the framework. Coaxiality was proposed, and we confirm. Zooming out for a while to see that we only have the coaxiality constraint with respect to the whole, we simulate the movement of the lever, and we actually don't have any other constraint. Let's now set another constraint, always simple but of coincidence. We position ourselves appropriately. Select the face and state that it must be coincident in abutment. So, anti-align, and in the options we see it's already anti-align with the face of the framework this way. By adding the coincidence constraint, the lever can rotate around the hole thanks to the coaxiality constraint previously inserted, and it's coincident to the structure in line with all the constraints placed, as we can see by simulating the movement of the lever. Let's now see another mating. We insert a new external reference component, lever. We insert it alongside, and here as well, we're going to run our matings. First mating, in this case, we try and use the inferred mode. That is, we select the bottom pivot of the lever component, and we get closer to the whole of the framework. The program proposes coaxial entities and coincident faces, so it applies directly both constraints. We click to position and confirm. Let's have a look at the history tree, at the model structure. We apply the coincidence anti-align and the coaxiality constraints to the first two components, lever 1 and framework. In the second one, the program automatically applied the two constraints of coaxiality and coincidence. In the history structure, the type of coincident is always specified, and if the offset between the two objects is 0, it's not indicated. Now, Let's go on and redefine the offset of the second object we inserted. So we add an offset of 25. How do we do? We select the coincident constraint, right-click, redefine. It proposes offset of 0, the default one, and we type 25, confirming. This way, the lever will rotate, but at a distance of 25. Let's now place another mating between the pivot of the first lever and the buttonhole to make it slide along the slot itself. Then, what do we do first? As always, we enlarge the involved area. Then we state object to be positioned, the inside face of the green lever, reference object, the type is not coincidence in our case but tangency, anti-align because we must slide, reference object, the pin, confirmation. If we switch to fit view and move the starting lever, we notice that by drag, that is, by dragging it with the mouse, we can see the movements of the objects respecting the constraints introduced so far. This is controlled by an option in Options Properties, System Options, Clipboard Drag and Drop, Preview Mode. The controls in this area enable to define the settings for managing the drag and drop operations of semi-constraints entities. In this case, it shows the preview of entities connected by mating. So, by dragging, the entities linked by mating will be dragged together, as we could see. Alternatively, we can set entities in multiple mating, but we haven't used this type of mating so far, or drag entity only, that is, if we move only the first lever, only the dragged entity is moved without considering the connection. So, let's set again the option in order to see together all the entities connected by mating, and dragging always the first lever, we double-check the movement, which takes into account the constraints we introduced. We now proceed by inserting another external reference component, a guide, that we place on top, over there. Then we insert the mating. First of all, we use the coincidence constraint, that is, we will need to make it slide along the top part of the framework. We enlarge the area, and as mating, we always used the inferred one. We select the bottom face of the guide. The type is still tangency, so we will have to switch it again to coincidence. Anti-align works fine, with coincident faces on the top part of the framework and coincident faces in the back vertical part. Then we must set offset to 0 because it remains set at the last value, and we confirm. By moving the guide, it slides along the top face of the framework, and it is coincident with the face itself, as we can see better from the front view. We position ourselves again on the previous view by 2 steps, and meanwhile we save the model that we are going to resume in the next e-tutorial as mating 1.